Okay, welcome back, students. In this video segment, we're going to look at a very popular method for finding antiderivatives for integration. It's called integration by parts. It's section 7.1. So let's begin. Let's begin with a question. How do we integrate? Not just in general, but how do we integrate things like x times the sine of x, or let's say integral of the inverse tangent, not the derivative of the inverse tangent. We know the derivative of the inverse tangent is 1 over x squared plus 1, or 1 over 1 plus x squared, but how do we integrate that function? How do we integrate the logarithm? The natural logarithm of x, not differentiate. The derivative of the natural logarithm is 1 over x. How do we integrate that? How do we integrate things like that first one, but say x squared e to the 3x? How do we integrate exponential functions? Let's say e to the 2x times trig functions, cosine 3x. All of these integrals arise in different settings in the sciences, in STEM fields. So we're going to attack a real important, a real popular, like I mentioned, method of integration by parts. At first, it takes some getting used to it, but once you get the hang of it and you see a sort of a pattern of what integrals fit this method, it works out really nice. Now, this method doesn't work out like any method. It doesn't work for every problem, but it works for a large class of problems, a large set of problems. So let's start with deriving this thing called the integration by parts formula. You're not responsible for the derivation, but I want you to see it. It's real quick. The derivation is based on the product rule for two functions. Let's say we have two functions, u and v, functions of x. So the product rule says the derivative of the first function times the second plus the first function times the derivative of the second. Okay. Now let's assume we can treat these derivatives like differentials. Like in integrals, we have dx or du, dv, whatever. Instead of derivatives, let's multiply both sides by dx and treat the quantities as differentials. So we get the differential of uv equals v du plus u dv. Okay, just bear with me. Then let's solve this equation for u dv. U dv equals d uv minus v du. Okay, now I want to integrate both sides. The integral of u dv is equal to the integral of duv minus the integral of v du. And finally, that middle integral we can simplify. The integral of 1 du with respect to uv, duv is just uv, minus the integral of v du. Everything except for that last line, is secondary. That last line is the most important thing. That last line right here, that I'm going to highlight in red, is simply the most important thing. This is called the integration by parts formula. Integration by parts formula. And for the remainder of this video segment, I want to show you how we use this, how we approach this. Now notice the integration by parts formula has one integral on the left and has another one on the right. So the main idea is on the left-hand side, you have an integral that is, say, a difficult integral. And you're replacing that integral with another one on the right. On the left, you have the difficult integral. On the right, you have one that's easier than the original one was. Okay, so somehow we replace the given integral, the one that's given to us is on the left, and with an easier one on the right. Now, you notice on the left, we start with the integral of u dv. We have to identify those two things. We have to pick, we choose u and dv. Okay, now a big question, a really, really big question, is how do we do that? How do we make the selection of u and v? Well, generally we do this, and I have another device for you after this, but generally we pick u as something that becomes easier. I'm going to leave that word undefined. Easier when differentiated, when we find its derivative. When differentiated. And we pick dv at something that is not becomes, but is easy, quote unquote, to integrate. I know this all sounds very strange right now because we haven't looked at any examples, but this is true. Let's start with the first one, the first integral I posed to you guys. Let's start with the integral of x times the sine of x with respect to x. So in this integral, we need to select, if we're going to use integration by parts, we need to select something called a u and then something called a dv. Well, we really only need to choose one, because once we choose part of this integral as u, the rest of it has to be dv. So we choose u that becomes easier when differentiated. So the choices for u are either x or sine of x, or the whole thing, x times the sine of x. Okay, those are the only things under our integral sign. So which one of these three things becomes easier when differentiated? Well, the first one does. The last thing, x sine x, if you use the product rule on that, it makes a mess. If you choose sine x as u, the derivative of sine is cosine. That isn't any easier than the original sign. But if you choose u equals x, the derivative or differential du is 1 dx, and 1 is simpler than x. So once we make the selection of u, dv is really selected for us. dv is the rest of the integral. And the idea was to choose dv as something that's easy to integrate. Well, fortunately, our choice for u as x leaves us with sine x, very easy to integrate. Integral of sine is negative cosine. Okay, so what do we do with those quantities? Well, the integration by parts formula says the integral of u dv equals u times v minus the integral of v du. Okay, so let's do this. What we're integrating is x sine x dx, so that's the u dv, and that becomes u times v. We'll look above in our little squared off the area there. We have u du, v and dv. Well, there's u times v is minus x cosine x minus the integral of v minus cosine x times du times 1 dx. And that last integral, minus cosine x times 1 dx, is very simple. This is just negative x cosine x plus the integral of cosine x with respect to x. So that leaves us with negative x cosine x. Integral of cosine is sine, plus sine of x plus a constant. And that's how the integration by parts generally goes. Notice that we did exactly what I said what was going to happen. We started out with a complicated integral, x times the sine of x, and we replaced it on the right-hand side with a less complicated integral, an easier to evaluate integral. So basically, integration by parts says replace a complicated integral with one that's simpler. There's some exceptions, but that's the general rule. Now that method of selection for u and dv, that's kind of rough. I mean, look back at what I said. I said we generally pick u and v, so that I'm putting it in green now so we can look back at it. U becomes easier when differentiated, and dv is easy to integrate. Well, that's subjective, and I think that might be a little slow for us to use in practice. So there's a device that I learned a long time ago. It's a really common device. I didn't make it up. I learned it from someone who was taught by someone else who was taught by someone. It's a little device for making things easier. So here's a device which I'll pass along to you for selecting u. Now this device is an example of what's called a rule of thumb. A very common expression, a rule of thumb. A rule of thumb is a rule that works often, sometimes real often, but not all the time. Okay, so this is a method that will work often for selecting u, and it goes like this: u equals Liate. And what you do is you read this device from left to right, and you go through your integral one letter at a time. You ask yourself, are there any logarithms in your integral? Then if there were, you would let u equal the logarithm, and then dv equals everything else. If there were no logarithms, you check for inverse trig functions. So if there were any inverse trig functions, you would let u equal the inverse trig function, and dv equals everything else. You look for, this one's a little strange, algebraic functions. Algebraic functions, another word for algebraic functions is powers. And they have to be whole number powers of x, like x squared, x cubed, x to the fourth, etc., etc. But not like x to the minus 1 or x to the 3/2 or whatever. So you look for powers. Then if you have no powers, if you have no logs, inverse trigs, or powers, then you look for trig functions. Okay. Then if there are no trig functions, you finally look for exponential functions. This device is really great. It's a rule of thumb that works very, 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 very often. So let's take a look at I gave you a series of integrals when we began the lecture. Let's take a look at the next one, the inverse tangent. So let's take a look at the inverse tangent. Consider, I don't know what happened there. Oh, here we go. Okay, so the integral of the inverse tangent of x. So we have our device, Liate. Let's do it. We ask ourselves, are there any log functions? Nope. Cross out L. Are there any inverse trig functions? Yes. There's a tangent. So I'm going to let u, we don't use the rest of Liate now, we just let u equal the inverse trig function. Then dv equals the rest. The only thing left is dx. du, the derivative of the inverse tangent is 1 over 1 plus x squared. The antiderivative, if I to go from dv to v, I find an antiderivative of 1 dx, if you will, I get x. And you notice I didn't put the constant of integration in there, so just leave off the constant of integration until the very end. So, our integral of the inverse tangent of x, that's our u dv, and that must equal uv minus the integral of v du. We don't have to write the formula in there. I'm just writing it to get used to it, so we get used to it. So u times v, x times the inverse tangent of x, minus the integral of v du. So we replaced our integral of inverse tangent of x with another integral on the right, x over 1 plus x squared, which is supposedly, or not supposedly, but hopefully easier than the one that we started out with. And it is. It's a super easy integral to evaluate. Let's use a substitution. I wouldn't use u or v for the substitution since our integral involves, our integration by parts involves those formulas. But if I let w equal 1 plus x squared, I get dw equals 2x dx. Or x dx equals 1/2 dw. So we're looking at x times the inverse tangent of x minus, make the substitution, x dx is 1/2 dw. And we're only left with 1 over w. And this is a massively important integral on the right with w. That's our logarithm. Logarithm of w plus a constant. Now, what did I make as a mistake? Just a second ago, I just wrote a mistake. Log of minus 1/2 log of w plus a constant. Did you catch it? Absolute values. Okay, you can't forget those absolute values when you find the antiderivative of 1 over x, or 1 over w in this case. So this is 1/2. Now look at what those absolute values are going to have to go away now. Look at how those absolute values go away now. Or do you remember why I'm doing that? Or why I can do that? Well, w equals 1 plus x squared, and 1 plus x squared is always positive. There's no need for the absolute values, and that's our integral. Okay, so what we're going to do is we're going to go through systematically those integrals that I started us out with. Let's take a look at the next one. Suppose I want the integral of the natural log of x, not the derivative. A very common mistake is for students to say that the integral of ln x is 1 over x, and that's false. False, 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 false. The derivative of log of x is 1 over x. So let's use our Lyautey device. Lyautey. Do we ask ourselves, are there any log functions? Yes. It's the only thing there, actually. So we let u, let me move this over, we let u equal the natural log. Not much left. The only thing left is 1 dx, or just plain old dx. Du, the derivative, is 1 over x, differential is 1 over x times dx. Antiderivative of 1 is x. So whenever you're going from u to du, you take a derivative. When you're going from dv to v, you integrate. So our integral, and again, I'm going to write the formula just because a lot of us are just getting used to this for the first time. It's u times v minus the integral of v du. I'm still getting used to it, and I've seen it for about 40 years. So I'm getting old. uv x ln x minus the integral of v times du. But look at the integral. X times 1 over x is just 1. I was going to write x. It's just 1. The antiderivative of 1 with respect to x is just x. Look at how nice that integration by parts formula works. When it's applicable, it works really, really nicely. Okay, sometimes integration by parts works, but there's more than just a couple of steps involved in getting the answer. And this is one of those things. Suppose we look at x squared times e to the 3x. I want to integrate that. So u equals liate. Ask yourself, are there any log functions there? Nope. Are there any inverse trig functions? Nope. Are there any powers, algebraic functions? Yes. So that tells us, our rule of thumb tells us to go ahead and make u equal to the power. Then dv has to equal whatever's left. Well, if I take out the x squared, the only thing left in the integral is e to the 3x dx. Du is 2x dx. And v, the integral of e to the 3x, is 1/3 e to the 3x. And leave off the constant. Okay. If you're not sure why that's 1/3 e to the 3x, you ought to stop the video and take a look at that. Yeah, the short story on that is you would let u equal new substitution w equals 3x, etc. So if you're not sure about that, you ought to stop the video and make sure you understand how I went from dv to v. So I'm going to push forward with our integral. So our integral of x squared e to the 3x dx is uv minus integral v du, or x squared times 1/3 e to the x. That's x squared over 3 e to the 3x minus the integral of v du. Well, v is going to have 1/3 e to the 3x, and du is 2x dx. So I'm going to get a 2 from the 2x dx, a 3 from the 1/3 e to the 3x. I'm going to factor that outside of the integral sign. And it seems like we have a problem. The problem is that last integral still has a power in it. Now, look what happened though. We started out with x squared times e to the 3x, and we reduced it at least by 1 to just x to the first times e to the 3x. Oops. 3x. Okay, so we reduce the power by 1. How are we going to get rid of that last power? Well, use integration by parts again. If we use integration by parts again, then we should be able to, seems, reduce the power or get rid of that x. So let's do that. Let's do integration by parts again, but only on the last integral. So on the last integral, I'm going to let u equal the x, the power, just like before I let u equal x squared. dv is going to be exactly what I let it equal last time. The rest. Phi is 1/3 e to the 3x. Du equals dx. So I'm going to bring my equal sign down. I'm going to have x squared over 3 e to the 3x minus 2/3. And then I'm going to apply the integration by parts formula. uv x over 3 e to the 3x. That's my little uv minus the integral of v du, v, 1/3 taken out, du. So that's my little integral of v du. Okay, now look at that very last integral. That very last integral has no more power, and it's super easy to integrate. So I have x squared over 3 e to the 3x minus, if I distribute the, I wonder if I want to do that. I was going to distribute the 2/3 in, but I think I'll save it for one more step. So x over 3 e to the 3x minus 1 over what? It's not going to be 1 over 3. It's going to be 1 over 9. If you're not sure about that, you should stop the video again and look at the integral of e to the 3x. E to the 3x plus c. So this is actually fine. Well, I guess we could do a little bit. We could do a couple of things. I'm not too picky with the answers in this case. So this is minus 2/9 distributing plus 2 over 27 e to the 3x plus a constant. You could leave it like that, or you could factor out the e to the 3x. In any case, that's our antiderivative. Let's take a look at our last one. This last one deals with a function, type of function that's going to occur early on in physics. When you guys take your physics courses as STEM majors, most of you are, you're going to study something called simple harmonic motion and dampened simple harmonic motion, that kind of stuff. And in that area, this kind of integral occurs frequently. So a combination of an exponential function and a trig function. This one's the roughest one, but it all starts out the same way. We select a u and then a dv. A dv would be chosen for us once we've selected the u. So we go through the list. Log functions? Nope. Inverse trig functions? Nope. Power functions? Nope. Exponential functions have powers, but the algebraic functions are powers of x. Trig functions? Yes. So u equals the cosine of 3x. dv is the rest. Okay. The derivative or differential derivative of cosine is minus sine. So by the chain rule, minus 3 sine 3x dx. Don't forget the extra 3 from the chain rule. The integral of e to the 2x is, let's see if you got it by now. What's the integral of e to the 2x? Well, it's going to have e to the 2x. Is it going to have times 2 or divided by 2? It's divided by 2, so 1/2 e to the 2x. So my integral of e to the 2x cosine of 3x is, I'm not going to put the formula now. I'm just going to write it out. But I'll say the formula out loud. It's u times v, so 1/2 e to the 2x cosine 3x minus the integral of v times du. Minus the integral. Well, du has a negative in it already, so plus the integral. Du has a 3 in it. Phi has a 2 in the denominator, so plus 3/2 the integral of e to the 2x sine 3x. Now what the heck, I'll put the formula in. This is uv. This is minus the integral v du. Okay, we have what appears to be a really serious problem. Integration by parts is supposed to take a difficult integral, which we start out on the left, and replace it with an easier one. Well, the integral on the left has e to the 2x times cosine 3x. The integral on the right has e to the 2x times sine of 3x. We've replaced our integral with another one of equal type. It seems like we got nowhere. Well, you're going to see in a minute that we really did get somewhere. The key is to use integration by parts again on the last integral, and a little trick happens. So if I let u equal the sine of 3x, again going through Liate, the first thing we hit is a trig function. Okay, if you need, Liate says you look for logarithms, nope, in the last integral. Inverse trig functions, nope. Powers, nope. Trig function, yeah. U equals 3x, sine 3x. So then dv in the integral must be the rest, e to the 2x dx. du, the derivative of sine is cosine, but by multiplied by 3 using the chain rule. Derivative of sine is cosine times the derivative of the inside 3. V is 1/2 e to the cosine e to the 2x. So let's continue. Let me move my equal sign down. So this equals the original 1/2 e to the 2x cosine 3x plus 3/2, and then in front of that, 3/2 will be the coefficient of using integration by parts with the new u and dv. U times v, 1/2 e to the 2x sine 3x. That's my little uv, minus the integral of v du. Well, du has a 3 in the numerator, dv has a 2 in the denominator. Integral v du e to the 2x cosine 3x dx. Okay, and again, it looks like we got nowhere. In fact, look at that last integral on the right. It's the integral that we're starting out with. Our integral, the integral we're looking at, is the integral of e to the 2x cosine 3x. It's on both the left and right hand sides. So what do? Well, bring all the integrals on one side. That's the trick. Take all the integrals, they're both the same integrals on the left and right, and they're not going to cancel out. We're not going to get 0 equals 0 or anything canceling out. If you don't see that, here's the trick. Let's get rid of the braces here. So this is 1/2 e to the 2x cosine 3x. Distribute 3/2. 3/2 distributes to get 3/4 e to the 2x sine 3x. Distribute the 3/2. So 3/2 distributed to the minus 3/2 gets minus 9/4. Integral e to the 2x cosine 3x. Okay, and that's my integral e to the original integral e to the 2x cosine 3x. When you're looking for the integral, isolate the integral. Solve for the integral. Bring the 9/4 integral of e to the 2x cosine 3x to the other side. Literally, just add it to both sides. So you have 9/4 integral e to the 2x cosine 3x plus the original integral e to the 2x cosine 3x equals that other stuff. I guess I could factor out the e to the 2x. I really don't need to. I'll do it anyway. 1/2 cosine 3x plus 3/4 sine 3x. Okay. Well, I want the integral. So add these two integrals together. How do we do that? Well, here's the answer to the question. How do we combine 9/4 a plus a as variables? 9/4 a plus another a. Well, we have to look for the least common denominator, so that's 4/4 a. Now combine them. You get 13/4 a if they were just variables. Okay. Well, we don't have 9/4 a plus 4/4 a. No, we don't. That a is not there. That a right there is not there. Get rid of it. What is there? I can't get rid of it. Let's see. I'm pecking at my screen like a... There it is. I guess it deleted it. We don't have 9/4 there. We have the integral of e to the 2x cosine of 3x. We don't have a here. Here we go again. This surface Here we are. Delete it. It's going to take forever to go away. Oh well. Bear with me. Okay, so we do have another e to the 2x cosine 3x. Okay, so 9/4 of the integral plus 4/4 of the integral gives us 13/4 of the integral. So we replace a with e to the 2x cosine of 3x. Okay, and what does that have to equal? It equals what's on the other side. It equals the e to the 2x times 1/2 cosine 3x plus 3/4 sine 3x. We can then multiply both sides by 4/13. Multiply both sides by 4/13. And we have, and then of course add the constant of integration. And we have our integral. So we have 4/13 times 1/2 cosine 3x plus 3/4 sine 3x plus a constant. And this little trick happens maybe 1 out of every 10 integrals. We need to do this little trick of getting the same integral on both sides and then isolating the integral. And that brings us to the end of this section. It was a relatively short section. Go ahead and dig into homework on section 7.1, and I will talk to you all again soon.